In this video, we're going to do an example where we're going to use Green's theorem to more easily compute the circulation around a curve and the flux across a curve. So the example reads, I have some vector field, it's the vector field x squared in the I hat and xy in the j hat. And then I have some curve, which is the square whose boundaries are x at plus or minus 1 and y at plus or minus 1. So I can sketch what the region is going to look like over here. If this is the x and y axis, then I am talking about the square here. And I am going to specifically interpret this square as the square where I go around the path in a counterclockwise way. And that's compatible with the way it's stated in Green's theorem, where we're talking about the counterclockwise circulation, for instance. Now, we could compute the circulation and the flux without using Green's theorem if we wanted to. It's a little bit tedious, and the reason why it's tedious is that the curve is not, for example, just a circle, it's a square, and so it has 4 different components. So if you wanted to, you could go and compute out the circulation and you can compute out the flux as well using 4 different components of the curve, and then it would be having 4 integrals. You add those 4 results together. That's possible, and in fact, I even think it's a good exercise for you to pause and try to do it and see if you're going to match the results that we're going to do in this video, where we're going to be using Green's theorem. Okay, so now I want to go and do circulation, and let me just scroll back to my formula just so that I can remind myself of what it is that we're actually talking about. What I'm trying to do is look at the first one first here. So on the left-hand side is a line integral. I don't want to do that approach because the line integral would involve breaking it up into 4 different components. I want to use the approach on the right. So it's the double integral over the region of the partial of n with respect to x minus the partial of m with respect to y. Okay, so with that in my head, let's go up and look at what our field is. Well, our field, this first component is the m, and this second component is the n. So if I'm actually going to use the theorem, then my circulation, here I'll write its line integral form down first, this is the one we're not going to be using, is going to be equal to a double integral, and I'm going to put in my limits of integration in a moment. I want to get my integrand right first. It's the partial of n with respect to x. So n was equal to x times y. So the partial of xy with respect to x is just going to be equal to y. And then I subtract the partial of m with respect to x. So m is equal to x squared, and so its derivative is 2x. So that is my integrand, and I write dx dy. And then finally, what are my limits of integration? Well, because it's the square where the values are like x going from minus 1 to plus 1 and y minus 1 to plus 1, the result is just minus 1 up to 1, minus 1 up to 1. So this is a double integral. And what I'll remind you is that what we're going to do is the inside integrand first, if we can, and then we'll do the outside integrand second. So the first one is the integral with respect to x. And so I'm going to put the minus 1 to 1, the far outside, and I'm going to put the dy, and I'm just going to be doing the integral with respect to x first. The integral of y, which is a constant with respect to x, it integrates out to being yx. And then integrating out minus 2x is going to give minus x squared. And then all of this evaluated between x equal to minus 1 and x equal to plus 1. And if you wish, you could even be pedantic about it and write the x equal to minus 1 and the x equal to plus 1 as well. Just be clear that this is evaluating it at x values. Okay, so we can do this. I'm going to plug in the values. It's going to be, well, I'll copy and paste the minus 1 to 1 and the dy. Nothing's changed there. But evaluating the inside, I had to plug it in at 1 and x equal to minus 1 as well. Plugging into 1 first leaves me with y minus 1. And then plugging in minus 1 gives me a value of y times minus 1, which is minus y. And then minus 1 squared, so then minus 1. And if I prefer, I can clean this up. So it looks like I've got a 2y, and then I have a minus 1, and then a minus is a plus 1, so that's it, 2y. And then, of course, this integrates out to being y squared between the values of minus 1 and 1, which is just going to give me the value of 0. This has 0 circulation. Okay, so that's kind of interesting, but now let's go and compute flux via Green's theorem as well and see what that result is. And I'll go a little bit faster through this one. For the flux, it's now the integral along the curve of f dot n. Flux measures the degree to which it's going in the outward normal n, and then ds. And then what Green's theorem tells us is that it is the double integral over the region, and I've already figured this out for the circulation, so I may as well put in the limits of integration as well. The region went from minus 1 to 1 in the x and minus 1 to 1 in the y. then the integrand is the most important part. So Green's theorem for flux says, well, I need to integrate what the divergence is, which is the partial of m with respect to x and the partial of n with respect to y. I'm just going to go back on the side here and just remind myself that it was x squared in the I hat, that was your value of m, and xy in the j hat, that was our value of n, just so I can take my partial derivatives. Okay, so first up, partial of m with respect to x, which is going to be 2x. And then I add to that the partial of n with respect to y, which is going to be plus x. And then all of that integrated out dx dy. We can do the inside integral first, so I'll put a minus 1 to 1 of something or other dy, which we'll figure out. The inside is 2x plus x, which is just 3x. That integrates to 3x squared divided by 2 and evaluates between minus 1 and 1. And that inside also cancels out and happens to also give 0. I actually didn't intend both of these answers to be 0, but looking at the specific polynomial terms that I chose in the symmetric region, everything did happen to cancel out in both of these, and that's perfectly fine. Now, ultimately, whether you want to use Green's theorems to compute one of your line integrals, whether it's going to be a circulation integral or a flux integral, just depends on the complexity of the integrals that are involved. Sometimes we have a nice curve that's parameterized in a way that we can write down those line integrals and they're reasonable to compute by our old methods. Sometimes when you go and use Green's theorems and talk about the region, well, that's a double integral. Some double integrals are easy to do. Some double integrals are hard to do. Back in multivariable calculus, we saw all sorts of tricks for double integrals. Maybe you need to convert them to polar. Maybe you need to switch the order of integration. I mean, integration is a very challenging problem. So ultimately, don't get forced into one method or the other. It's going to depend on the challenges of the actual integrals that are involved to see whether or not you can solve it analytically in an easy way. But if you have this theorem, you have a bit of flexibility. You could stay with the line integrals when they are easy and reasonable, but you can also convert them to a double integral, and maybe that's going to be easier.